models, and then a bit what their advantages and disadvantages are. And then I will talk about factorization machines, and at the end about lots of applications. I will talk about applications from recommender systems, click-through prediction, social network prediction, student performance prediction, and something. Okay. Let's talk about factorization models first. I guess the most common and most well-known factorization model is matrix factorization. And the motivation typically is that you want to predict the interaction between two variables. So in this case, I have here a small example where you're interested to predict what kind of rating a certain user will want to give to a certain indeed. So that's one of the typical examples for matrix factorization. And as you see, some of these cells are observed, the green ones are not observed, and the green ones we might be interested in estimating. And the matrix factorization model, the idea is that the underlying matrix has a low-rank structure. So this means, in my case, I will always represent K as the rank of this underlying structure. And to write this a bit differently, I think this is maybe a bit more common from people who are not used to matrix factorization model. Maybe this notation is a bit more familiar. So you can say, if I want to predict some target variable between two variables, I assume that for every user in this case, that every user can be represented by a latent vector of k variables, every item can be represented by a latent vector of k variables, and the dot product between the two of them should explain what the underlying concept is. So, and the interesting thing is of such factorization models is that even though you don't observe some interactions, you can still estimate the interactions. So if we learn, for example, the factors for user A, we would learn it from his first three interactions, and we would learn the factors for the item ST from the interactions that we observe. Then we can estimate interactions that we don't observe, because we can just build a dot product between these two latent vectors. And that's the basic idea for factorization. Unfortunately, it's not that easy if you want to get the best prediction quality out of it. So matrix factorization is typically a great approach if you have two variables. But even in this very simple case where you have two variables, people came up with different models that work in some applications better than this standard matrix factorization. So for example, people from Netflix Prize came up with these SVD++ and factorized nearest neighbor models. I don't want you to understand these equations, so just what I want to show you is to design a factorization model that works best on a data set. It's not just applying matrix factorization. So there's a lot more work that you might have to get the best results. So these two models that you see on the bottom were used by the Netflix Prize winners. Things get even more complex. Typically, you are not interested in just problems where you have two variables, but you have much more variables. You might have tens or hundreds of variables. And then all of a sudden, it's not so clear how you solve this with a factorization. And so to give you a very simple example, let's assume we have a third variable at time. So this is something that is in almost every data set that you collect. So it's a time variable. Then all of a sudden, you have a matrix that changed over time. And there also people came up with many different kind of factorization models. Some work better than others, and some work better in one data set, but worse in the other data set, and so on. So it's what I want to show you, it's a bit complicated. Even more so, some other examples, if you have tensor data, there are different models for tensor factorization. Again, besides of standard tensor factorization models, you can derive also more specialized tensor factorization models for specific problems. You can derive sequential factorization models and so on. So what I wanted to show you here is two things. First of all, the advantage of factorization models in general is that you can estimate interactions between variables even though you don't observe this particular observation. So this is something very important. And they are especially good for things where you have interactions between two variables that are very large. So, for example, all the users that you have, all the movies, all the websites, and so on. So between two very large variables. Okay, and the downside of factorization models is, I mean, typically they work pretty well, and they achieve in many competitive settings very good prediction quality. But to get really the best results, what people typically do is they define factorization models particular for that problem. So they really tailor them for their problems. And this means you need a lot of experience to apply this. So you first have to derive somehow your model equation, like all these equations that I showed you before. Then you have to derive learning algorithms for them. And if you want to do experiments, then maybe you have to change your model again and derive a new model and then start from scratch. So this is something very complicated, and only people who have a lot of experience in these things can do this. Even for them, it takes a lot of time. Okay. So if we think of, on the other hand, how I think machine learning problems are typically unsolved, especially in industry, is that you say, okay, I take a toolbox, and I treat the machine learning algorithm somehow as a black box. Like, for example, if you think of linear or polynomial regression. So typically, what you do is you define your problem with a real value feature vector, so you do feature engineering, you feed this into your black box, your machine learning tool, you get some predictions out, you check what happens if you put different features in, and you see at the end result, and you have your loop, and more or less what you do all the time is feature engineering and see what at the end what you get. And this is a very flexible approach, so you can deal with any number of variables, so nobody's frightened if you say I have, instead of 20 variables, 21 variables. Many different kind of variables you can treat very easily. So for factorization models, it looks a bit like they are only good for categorical variables, but what do you do with things like real value variables, like income or let's say time or things like that. There it's not so easy to do. Also with set categorical variables and so on. If you do this kind of generic way to work with a machine learning model, you can apply a large variety of machine learning models, like linear regression, SVMs. All of them work with the same way. You do feature engineering, you feed it into your machine learning model, and you get something. I want to talk now a bit about what the disadvantages is of these approaches, because otherwise there wouldn't be a reason to do all these kind of complicated factorization models. So let's have first a look at linear regression. I think all of you know it, but just that we have the same location in mind. Linear regression, as other machine learning models, you assume you have a real value input vector x. Might be hundreds or millions of real value variables. And your model equation is you assume you have a linear effect between your input and your output. So for every variable that you put in, you estimate a parameter, how much this variable has an influence on the output. So it's a linear model as well. It's called linear regression. And what you do is you basically have to estimate p many variables. So if your input vector has a million entries, then you have to estimate a million variables. So for our example from the beginning, if you have a movie recommendation website, what you could estimate it, for example, if you have as input variables the movie and maybe, let's say, the gender of the user, you could estimate that this movie in general is a good one. So the movie in general gets high ratings. And you can estimate things like the certain demographic, for example, certain age group in general gives higher ratings than others. But you cannot estimate that a certain demographics like this movie but don't like another movie. So you don't have interactions between the two variables. So you can only estimate single effects. What people usually do then to estimate also cross effects, like this particular movie is good for older people but not so good for younger people, is you add crosses between the variables. So you effectively polynomial regression model. So for every two variables of the input, you learn one more variable. So if you, that means if you have the input a million variables, then you would learn a million very many effects. So you could learn this movie is particularly good for younger people, but not for older. Yeah, so one short side note, typically you don't have a polynomial regression model implemented, but you would use a linear regression model as the implementation into this dot product between these two in the feature engineering step. But the underlying concept is the same, and it's important to introduce it like this, that you later on see how the factorization machine. But this is just a side. Okay. So after we've seen now linear regression and polynomial regression, and in the beginning the factorization models, I want to talk a bit about how they compare and in which settings it's not so good to apply a linear polynomial regression. Okay, first of all, the example that we've seen in the beginning, we all know that a factorization model will work great. And I want to show you now that for this application, a linear polynomial regression model will fail completely. So it's not a problem of representing the problem. So you can easily represent this problem with a feature vector, with design matrices. So this is what I want to show you first. So this is the representation that people usually use when they apply factorization. But you can for sure easily translate it also to feature vector representation. So the things on the left and the right is the same thing. One is have the entries of the matrix listed, but the information in these two things is the same. It's just a way of looking at the same problem from two different points. And this is much closer to the way of data that you would feed into a linear polynomial regression. Typically, as I stated before, you need your input should be a real valued vector, so this is not a real valued vector yet, but with a standard approach of using one-hot encoding, you can get this thing into a real valued representation. So again, this and this is a step that this is the most common to transfer such data into real valued vectors. And just to give you a short idea how it works, so I guess most of you know already, but you would use for every kind of level of the user variable that you have, you create one binary variable, and for every possible value of the movie variable, you would create one possible level or one possible binary feature, and then to represent this first line, you would activate the binary variable of Alice and the binary variable of Titanic, and the rating is still 5. And you can do this for any example. You can represent it as a real value vector. So you need this transformation because linear regression works with the real value vector and not with categorical vectors. And this is the standard way to switch between these two representations. I think some machine learning tools might do this automatically for you, but this is what's happening now. Okay. And for sure, this thing you can feed now into a support vector machine, a linear regression, polynomial regression. So let's have a look what happens actually. So if you apply such data to a linear regression model, the linear regression model would behave the following. So you would have for each, so in each of our example data that we have one user activated, one item activated. So the linear regression model would output the effect of the user and the effect of the item. So that's what the linear regression model would do. And there you can see you cannot estimate any cross effect. Okay? So you can say this user gives high ratings in general, or this item in general receives high or low ratings. You cannot say anything about the particular taste of the user or not. So this is not very expressive. So it's very easy to estimate, but it won't give you good predictions. On the other hand, we said with polynomial regression, you have now all interactions between all pairs of variables. In this case, you have only one pair because all the other things are 0. So we would have additionally a variable for a certain user and a certain item, which is great. So the model can express that this certain user likes this certain item and doesn't like the other item. But the problem of this model, of the polynomial regression model, is you can express it, but you cannot estimate it from your data. Because for this particular variable, so you have now p square many variables. So if you want to estimate, for example, let's go back. For this example, you would have a parameter for Alice and Titanic. You would have a parameter for Alice and Nottingham, one parameter for Alice and Star Trek, and so on. But you know you can only estimate your parameters for data that you observe. So you could for sure estimate the parameter for Alice and Titanic because you observe it, but this is somehow trivial. But you cannot estimate the parameter, this W of Alice and Star Trek, because you have no training data. Okay. So the problem of this model is, if you apply it, you can represent it, it's very expressive, but you cannot estimate your parameters for it, because you don't have any observations for the parts that you're interested in. So you're interested in estimating the interactions of the user and the item that you don't observe. And for this one, you don't have observations, so you cannot estimate. So effectively, this polynomial regression model would be as bad as the linear regression model, because you cannot estimate any interesting effect. Compared to if you would apply matrix factorization, as we have seen in the beginning, there the trick is you can estimate interactions between two variables because the parameterization is independent of both of them. So your parameterization is you learn something for the user, you learn something for the item, and then you can do any combination that you want, even combinations of things that you don't observe. And this will work as soon as the underlying data is a lower k. This is your model assumption. And in many, many cases, this holds system. So this is the important part where you see, or where you hopefully see, where the real benefit of factorization models comes. This is just what I said before, but it's important, so I will repeat it once again. So in this particular case that we have seen, the linear regression model would be not expressive enough to estimate anything that you are really interested in. On the other hand, the polynomial regression model would be very expressive, but you cannot estimate it. Don't forget the formulas. The important part is the last bullet point. You cannot generalize anything that you can observe. Okay. Now I want to talk about factorization machines that combine these two approaches. So I guess we have seen that factorization models in general are good to estimate these interactions. On the other hand, they are complicated to apply to problems. On the other hand, linear regression models are very easy to apply to problems. You don't just do your feature engineering and then you're done. And factorization machines combine these two. And I think now after we've seen this long introduction, it's a very small step to the factorization machine model. Actually what you do is, and I think I introduced it better like this, on the bottom you see the polynomial regression model that we have seen before. Okay. And on top is the factorization machine model. So both of them, as you can see, are very, very similar. You estimate single variable effects and you estimate all the effects between all pairs of variables. But the important difference is how these variable interactions are parameterized. So in the polynomial regression model, we would have p square many variables to estimate, and each pair in a polynomial regression model, so wij and wil are completely independent. They have nothing to do with each other, even though they share the index I. In a factorization machine, you would assume that this thing has a lowering representation, and that's how you smooth somehow, or you generalize over your pairwise interaction. And there you can say, for example, the interactions between ij and I and L definitely have something to do together because they both share the real I. In this case, wij and wil don't share anything. So knowing something about wil doesn't help you anything to know about wij. In this case, it Okay, that's the basic idea of a factorization machine. So you can deal with it like with a polynomial regression model. You can do all kinds of feature engineering and can enjoy somehow this possibility to generalize between modules. Okay. For sure, you can also do this for interactions between more than 2 variables. You can do this for 3 variables, for 4, and so on. In this case, you would replace this part with a matrix factorization. You would replace it by tensor factorization. For example, this one is the canonical decomposition model. And you can do also the same thing with 4 or 5 instances. But everything that I show you today is just with the pairwise, and in general, this works already pretty good. Okay. Yeah, so far to the introduction of factorization machines. As you have seen, they work with real valued input as a linear regression. So if you don't know that this, if you don't know what's in the black box, you don't really realize that you work with a factorization machine. It looks like you're working with a linear regression or polynomial regression. So you can do all kinds of feature engineering and treat really the learner or the algorithm as a black box. The way factorization machines work with the variables is very similar to polynomial regression. You add all the interactions between all input variables, but the important difference is that the interactions of the parameters are bigger. There you can also see that you get a much smaller space of parameters to estimate. In a polynomial regression model, as I said, you have p square many variables to estimate. Here you would have k times p, and k is mostly in the order of like tens or hundreds, whereas p might be in the order of millions or billions. So you see you somehow reduce the number of parameters, and this allows you to smooth out internally over. Yeah, what I want to show next is, I think it's pretty clear that you can work with a factorization machine like linear regression. The more interesting part is how does it compare to all these factorization models that we've seen in the beginning, because we know these are great models and they have shown great performance on things like the Netflix price. And I want to show now that you can do very easily with factorization machines, you can do the same thing as with these models that you derive by hand. So the simplest example, let's go back to the case where we just have 2 variables, 2 categorical variables we would feed into a factorization machine, and the factorization machine would behave like this. So you would have for every variable that you feed in, one effect. So in this case, we feed somehow only 2 non-zero variables. We would have one effect for each of them, and you would have one effect between the interaction between these 2 variables. So this works basically like a matrix factorization. If you feed 2 variables in it, you will get the same result out as a matrix factorization. If you feed 3 variables in it, you will get like all the pairwise interactions, all the factorized pairwise interactions. And this model was proposed before for the ECML 2009 Discovery Challenge, and that worked pretty well and was awarded the first place. So just by doing a very simple representation of the factorization machine, you get the same thing out as this video. Now what I want to show next is like how you're supposed to work with a factorization machine is by feature engineering. So for example, you would have user variable, item variable, and time variable. Time you can see in many ways. You can say time is something, is a number which has a linear effect. So the longer the time, the more popular the product is, for example. If you think this is the case, you can input the time as a numerical value. For example, odd seconds since the system began. If you think the interaction is a bit more, or time is a bit more complex, maybe you want to bin the time, then you would bin the time and you feed it in the factorization model, and you would get a model that works like the following. And this actually works pretty well on the Netflix price. So, very simple, just bin the time, add it as an additional variable, and you get a very nice value of the Netflix price. And you can do whatever feature engineering you want. So these are just 2 examples. In the beginning, we have seen this SVD++ model, which worked really well on the Netflix price. Yehuda, one of the winners, used this in his final solution. you can see it as the following. You have actually three variables, the user and the item variable, and another set variable. And the set variable is all the movies that someone has watched in the past. So this variable is likely to be interesting, so you can just add all the movies that someone watched in the past, just activate all the movies that someone watched in the past. You feed in the factorization machine and it works like SVD++. So this part of the factorization machine would be exactly what SVD++. And you get some additional interactions. And yeah, if you apply this, you will get also very good result. And for sure, you can combine all these things. So you can also add your time variable and so on. Without, it's just repeat. You can do sequential models like you have often in online shops. After you buy this, you will buy this. After you buy this product, you will buy the other product. These are just a few examples that you can see. With a factorization machine, you can get similar results to well-established factorization. I want to talk shortly about the properties of the factorization machine. So if you look at this model equation, it looks on the first glance a bit scary because you have these nested sums, 2 times the nested sums of p, and there's actually a dot product, which is the sum of k things. So it looks like computing just this equation is p squared times k, which looks a bit frightening. But actually, you can do this much more efficiently. So you can compute this efficiently in p times k. So by just rearranging some sums. I don't want to go into the details here. It's actually not so complicated, but if you want to see the proof, it's better to do it with paper than if I show this instance. Another thing is typically when you want to apply a factorization model, the input vector is very sparse. And in this case, you can further speed up computing this part because you only have to iterate over the non-zero values. So you don't have to go over the zero values because 0 times something is anyway 9. So, actually, you can compute this whole equation in the number of non-zeros in the input vector times your factorization. Compared to a polynomial regression, there you would have p squared, or number of non-zeros squared many operations. So I will skip the proof if you are interested in look it up. The other nice property of the factorization machine is multilinearity. So if you just use factorization machine as a black box, you don't have to care about all these things. But if you think of extending something or writing your own learning algorithms or something like this, then it's good to have these properties in mind because they make your life easier. So a factorization machine is multilinear. That means for every parameter that you want to estimate, if you pick this parameter and fix all the other parameters that we have, the factorization machine is a linear equation. So if we pick out from all the parameters that we have, and there are usually a lot of them, if we pick out one of them, then we can write the factorization machine as a linear function. So here you have 2 parts that are independent of theta times theta. And this helps you a lot if you want to derive learning algorithms, because things like coordinate descent algorithms, Gibbs-Semper, and so on, they are very easy for linear equations. Again, I will not go into the formulas too much, so if you want to see this, you can look at it. Now about learning. So after you have these kind of properties, it's very easy to derive learning algorithms. So for factorization machines, for example, stochastic gradient descent has been proposed, coordinate descent algorithms, Markov chain Monte Carlo algorithms with Gibbs sampling. So these are algorithms for regression and classification. You can also do ranking. So there you can do, for example, stochastic. And yeah, all these algorithms, if you implement them properly, you can implement them very fast. So they have a runtime of the number of non-zero in your original problem times the factorization dimension. So, which means you have somehow a linear amount of work that you have to do in your input. So you have to go once over your input, and how often you have to do it in some time. Actually, you can do it even faster than this thing in case your underlying problem has some structure, but I won't go into this. Yeah, I won't go into details about these learning algorithms. They are quite standard to derive them if you use the linear property of the problem. So I will just skip these things. One thing I will talk about, because I will use it in the application several times, is if sampling and two-level models. So typically, if you work with a learning algorithm, there's always the problem of overfitting. So you're afraid that you fit your data too much, so that you have a low prediction error on your training data, but a high error on your test data. So the typical way to resolve this is to add regularization of priors on your model parameters. And one way is to do, for example, normal priors with L2 regularization. And then you somehow solve this problem, but you have to choose the right parameters for your regularization, otherwise still you might overfit or underfit. So practically what people typically do, they choose one regularization value, learn their whole, or train their model, then they choose another one, train the model again, choose another one, train the model again, and in the end they keep the best. And this is very time consuming, especially if you have a lot of regularization values, and this is of course exponential. What you can do to solve this problem is to make the inference over your regularization parameters in your model. So this you can do with a two-level model. So in this case, I would have included your lambdas, your regularization values, into the inference. So you learn your model once, and it learns automatically your regularization values and your model parameters in one shot. And this is what I will use in the application. So one note. As I said, you can treat factorization machines like a black box, and there are several implementations. One implementation of factorization machines is libfm. It has second order FMs with the learning algorithms that I showed you before. You can do classification, regression with it. It has the same input as libsvm or liblinear, so if you have data for this tool, you can come directly apply. And it's open source under G. So let's go to some applications after all the theory. The first application I want to talk about is recommender systems, because it's one of the traditional things where people know factorization models. But I will also talk about that. So in rating prediction or context-aware rating prediction, this is also no problem with factorization machines. You have mainly two variables, user IDs, item IDs, and then a lot of additional variables, often like time, mood, user profiles, item profiles, location, and all that. Popular examples for these kind of problems are Netflix price, KDDCup in 2011, and so on. And I want to talk a bit about the Netflix price, because I think this is one of the most well-researched data set, and there you have really, really strong data. And I want to show you here what you can do with a factorization machine and just with feature engineering, and treating it as a black box. So you see here the scores from the Netflix price. So these are arrows, so the lower the better. And I have here the result of SGD matrix factorization, which is already a quite good model for the Netflix price. So the original baseline of Netflix would be somewhere here, like it's 95%. And what I want to show you here is if you just put in a user and a movie variable into libfm, you would get this kind of error. If you put additionally the day in it, you drop more. If you use instead implicit rating, you are here. If you put both things in it, you end up here. If you do some more feature engineering, and so on. And all these results here are obtained with a 120 28 factor dimension. And I used MCMC inference, so I didn't choose any hyperparameters. So I didn't choose any regularization values, no learning rates, and so on. Okay. So, this part here. And yeah, so I want just to go quickly through several